Any questions? Nothing? About the homework? There was homework posted, wasn't there?
Yeah.
Did you have any questions at all about it? Nothing at all? Okay. Well, so we were beginning at the end of chapter 5 in propagation, and I'll tell you about that. I've got a few things to mention. So we came down from Maxwell's equations down to this, where we had del squared of E plus gamma squared E equals 0, and let's see here, or minus gamma squared. Pardon me, this is minus gamma squared of E equals 0, and then the solutions to this, if we assume that sigma is 0 and that the divergence of D equal rho V equals 0, not sigma equals 0, but if divergence of D equals rho V is 0, then we get things that are called plane waves. And plane waves have solutions of E in general equal to some E naught plus E to the minus gamma Z plus E naught minus times E to the plus gamma Z. And we put these in the AX direction. The wave is propagating in the Z direction. And since gamma was equal to alpha plus J beta, we can further state that E is equal to E naught plus E to the minus alpha Z times E to the minus J beta Z. Let me get this a little better. E is equal to E naught plus times E to the minus alpha Z times E to the minus J beta Z times, or in the AX direction, plus E naught minus E to the alpha Z times E to the plus J beta Z AX. I'm trying to get that up there as fast as I can. And I broke out gamma as alpha plus J beta. Now that's a plane wave with both a positive traveling wave, this is going in the plus Z direction, and a negative traveling wave in the minus Z direction. And that's in the phasor domain. If we go ahead and we find E in the time domain, and Z comma T, that's going to be the real part of this, and I'll call it a phasor, E vector phasor times E to the J omega T. Remember how we did this when we did transmission lines? To go from phasor to time domain, you multiply it by E to the J omega T and take the real part. Does everybody remember this? This is real important because you're going to see this so many times. So in the time domain, this will become E is equal to some E naught plus times E to the minus alpha Z times cosine of omega T minus beta Z here. And it's going to be plus E0 minus times cosine of omega T plus beta Z here. And these are both in the AX direction. That's the orientation of the wave. And here, this is a traveling in the plus Z direction. This is traveling in the minus Z direction. Does everybody follow me on this so far? So I'm just showing you both. This is the equation it came from. Based on this assumption, we're talking about plane waves. So really, E has only an X component. And it's only traveling in the plus Z direction. But we went through that. Now, when you take a look at this, I'm going to just mention a few things that you have to be aware of. If we forget the one traveling in the negative direction for a moment, we just focus on a wave traveling in the positive Z direction. So this is going to be plus Z direction. Then sum E naught e to the minus alpha z, right there, times cosine of omega t minus beta z, ax. Now, we have to, from this, find a few things. Do y'all follow me on what I'm doing here, class? This is what we did last time, right?
We were wondering what happened to the second E in the negative Z wavelength.
Oh, right here, this should be, yeah, e to the gamma z times E naught minus, my bad on that one. You're absolutely right, Bob. This E naught minus is just the magnitude of the electric field that's traveling in the negative Z direction. Now, usually we just focus on positive Z directed waveforms. That's where I wanted to get to start, right here. Now, at this point, a couple of things we have to get. One is the phase velocity from this. Now, you all remember what phase velocity is. Really, if you have a wave traveling, and I'm going to go over here and do this. If I have some wave like that, and it's traveling this way, then this point is at a constant phase. The argument of this would be cosine of omega t minus beta z. You can think of it that way, and this could be the actual z direction here, and this could be just some amplitude a. But this is an expression for phase. You follow me? I didn't write the whole cosine waveform, didn't show the whole thing, but here's the actual phase of the wave. Do you follow me? Now, if that phase is 0, this would have a value of 1, correct? And if the phase here was equal to pi over 2, it would be 0. And if it was minus pi, it would be minus 1. It would be a waveform. But constant phase will tell me either, I could say the peak of that waveform, I want to see how fast it goes. So what I do is say for phase velocity, I allow the phase of t to be equal to omega t minus beta z here. And then I take a derivative of that with respect to t, and I get omega minus beta times dz dt. And if you want to find out how fast the crest of a wave moves, well, then you want to see how fast the point right there of constant phase is moving. So there is no change in phase. Do you follow me? Here is how you get it. You set this equal to 0. When you set that equal to 0, then you find that dz dt will be equal to, take minus omega by minus beta, so it's omega over beta. And that's true always. And that is the phase velocity, by the way. That's v phase. Phase velocity. Very important. Now, what you can say is this also. If, and only if, the media is lossless, if media is lossless, or sigma is 0, that's another way of saying it, lossless media, then you can see that gamma, right here, gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. And that's alpha plus j beta. Y'all remember this now? All right, well, if sigma is 0, then gamma would be equal to what? It would be just j omega u times j omega epsilon, right? So that's j omega squared, and the square root of j omega squared is just j omega. And then it would be times square root of mu epsilon. And that would be equal to simply j beta. And here, alpha would be 0. There would be no attenuation. So this is the lossless case. Follow me on this, guys? Right? Now, if it's lossless, if it is lossless, then when we look at this, since beta, therefore, for a lossless media is equal to omega times square root of mu epsilon, you can see that the phase velocity for a lossless media, this is only for lossless, is omega divided by beta, or it's simply 1 over the square root of mu epsilon. You all see that? That's for a lossless case. All right? Another thing, we sometimes, I don't do this, but I think it's valuable to do this. The next thing we want to talk about is the wavelength. So what is the actual wavelength going to be? Well, do you remember how you get wavelength? First, you look at the equation that expresses the behavior of the field, right? And we can do this for a lossless and a lossy case, but I think right now we're going to stick with lossless. We're going to do this for losses. Well, in general, if you look at this, we have E for the lossless case, and we're looking at the wave traveling in the positive z direction. That's E0 plus cosine of omega t minus beta z, and the AX direction can be put down. So now we do something. Since we want wavelength, we're going to let t equal to 0. We're going to freeze time at 0, and we're going to look at spatially how it varies. And here, E would be equal to simply E naught plus times cosine of technically minus beta z AX, right? But what do you know about a cosine waveform? Cosine's an even function, right? So cosine of minus beta z is the same thing as cosine of beta z. Do you follow me on that? So just make it plus. Then graph that versus z. And what you see is this. It's going to go start here, it's going to go down to a minimum if this is 0, and come up. And this distance right here would be equal to beta z equal to 2 pi. Do y'all follow me on that? Because this would be a period. Do y'all see that? All right, now that z that makes this happen, the length over which it takes to repeat itself, that is the wavelength. So you put a lambda there, because that's the symbol for a wavelength, and you see that lambda is therefore 2 pi over beta. And that's the same thing it is for when we did transmission lines, if you remember. And actually that's true even if it isn't lossless. That's generally true. Okay? And remember, when we talk about wavelength, we have to have a constant frequency. We can't talk about wavelength for something that is made up of an infinite number of frequencies, like a pulse. It makes no sense. So that's wavelength. Now, a couple other things happen. Let me take out this part of the board. I understand this weekend's going to be all rain. It's at least what the weather forecast was last time. I wish it wasn't so. Now, next thing, we had an equation. Remember, we had the del squared of E equation minus gamma squared of E and equals 0, and that rendered, I'm not going to write the whole thing, but in general it rendered, let's just do the plus Z solution of this. E is equal to some E naught plus, right here, and then it's times E to the minus gamma Z AX. And I'm just doing the positive traveling wave because I don't want to make this too, the negative traveling wave, the effects are the same, and it just gets a little bit cluttered with what I'm about to do with all that. Now that's the E field. By the same token, if we have the Maxwell equations, we have curl of H is equal to sigma plus j omega epsilon times E, and curl of E equals minus j omega mu times H. Remember what I'm doing here. I'm replacing J with sigma E, D with epsilon E, and B with mu H. Follow me on this, everyone? And then I'm putting in the phasor domain. When I take this, if I wanted just one equation in H, not E, then what I could do is take a double curl of that one, and I would get curl of H here is equal to sigma plus j omega epsilon times curl of E. You follow me? With me on this one? Then, I'm just taking a double curl of this equation now. Then I replace curl of E with this, and I'll break this up as the gradient of the divergence of H minus del squared of H is equal to, and then it's sigma plus j omega epsilon here, and then you're gonna have, I like to put this up here, minus j omega mu here, and then H, right? Because when I substitute curl of H with this, take this for curl of H, I get this. Well, by definition, what is the divergence of B equal to by definition? Do you remember this? This is a very important thing. Let's try this. What's divergence of D in general? Divergence of D. Rho V, the volume charge density, right? Now, volume charge density means there is electric charge, right? What is divergence of B equal and why?
0.
It's 0, but why? You're right.
You don't.
There is no magnetic charge. There's no magnetic monopole, single pieces of magnetic positive charge. So divergence of B is 0. Because B is equal to mu H, and mu's a constant, divergence of H necessarily is 0. Do you follow me on this, class? And because of that, this goes away. Now I'm left with that. What is this term right here that I'm circling? Gamma squared, exactly. So now we can get a single equation in H. We can have del squared of H minus gamma squared of H equals 0. Same exact equation, same form as the electric fields equation, right? Right here, right there, right? And we came from Maxwell's. And the solutions to this are the same. And I'm going to say the H field, and I'm only going to give it for the positive Z form, or really, we're only going to talk about H field moving in the positive Z direction. That would be equal to some H naught positive e to the minus gamma Z. It would be in the AY direction. It has to be perpendicular to the E field and the direction of propagation. I'll get to that in a minute. Now this E field and this, this H field and this E field exist at the same time in space. As a matter of fact, you cannot have a propagating E field without an H field, necessarily. And it comes from Maxwell's equations. These two equations, when you solve them, and it doesn't matter what coordinate system it is, and it doesn't matter if it's going to be steady state or really, if it's a time-varying phenomena that creates a propagating electromagnetic field, or if there's charge acceleration that creates the field, then E and H are linked, and they're inseparable. As a matter of fact, what you get is this. If you have an E field in this direction, you'll get an H field that's perpendicular to it, and it will be perpendicular to the direction of propagation. And you use your right hand to get this all the time. This is something you get used to. Take your right hand, put your index finger in the direction of the electric field, and then use that as a hinge thing where your thumb is, and in the shortest angle, just curl or use the wiper arm and wipe it into the H field. So E crossed H, your thumb points in the direction of propagation. You follow me on that? Furthermore, the actual power, the instantaneous, or the power in general, P av, is equal to 1/2, and normally if they put this 1/2, the real part of E crossed H conjugated. Now, this will come down to, when you have E crossed A conjugate, you're going to find this out, but you're going to get, well, let me put it to you this way. If this is my H field and this is my E field, when I cross them into each other, I get AX cross AY or AZ. Do you follow me on that? So the direction of energy transfer would be in the Z direction. I can write this out. So this is going to be equal to 1/2 the real part of E, right here, E naught plus E to the minus alpha Z, E to the minus J beta Z, AX crossed into H, and H is going to be H naught plus e to the minus gamma z, e to the, but H is conjugated here. And I'm just gonna tell you one thing. Do y'all remember back in the day when you had circuits? Do you remember how power in circuits, average power, was equal to 1/2 the real part of V, right? Dotted with I conjugated. Do you all remember that? The I was conjugated? Well, when you conjugate the H field, right, that means the J beta would reverse signs, and instead of minus J beta, it would be plus J beta Z in the AY direction. Are you with me on that? Now what happens here? That means my PAV right here will be equal to 1/2, and then I'm going to have E naught plus magnitude of that times magnitude of H naught plus, and then I have e to the minus alpha z times e to the minus alpha z is e to the minus 2 alpha z, and then e to the minus j beta z times e to the plus j beta z is what? It's 0, isn't it? E to the 0 is 1. And that means AX crossed AY is AZ. And that's the power flow, the average power flow. But now we're going to relate E to H, E naught to H naught. And this is a real important value. You're going to see this all the time. So when we take a look at the relationship between E and H, I have the curl of E, or better, yeah, curl of E is equal, curl of E is equal to minus J omega mu H. Well, I can do this kind of quick, but you know, the curl of E is what? Curl of E can be rendered as AX, AY, AZ, d dx, d dy, d dz. You don't have to write this down. And then it's EX. Remember, there's only an X component. These two are zeros. Correct, class? All right, well, what's that curl of E going to be? Curl of E would be AY d dz of EX minus d dy of, well, actually, minus, hold it, yeah, d dy of EX AZ. Since E does not vary with Y, this goes away, and it's just the derivative of EX with respect to Z. Follow me on this? In the AY direction. So this curl of E is in the AY direction, and since this is the E field right here, I'm only doing this for the positive traveling wave. Taking the curl of that just brings out minus J, or minus gamma right there. So it's minus gamma right there times E naught plus e to the minus gamma z here is equal to minus J omega mu times H naught plus e to the minus gamma z AY. And really the only thing I've done, I'm trying to move along here, is just take the curl of the E field where this is the E field. It's the solution. It's only for the right traveling wave. Okay, class? Now when you do this, there's something real important that comes out of here. Can you all see, looking at this, that I can cancel this? These two cancel, right? And furthermore, the AYs cancel. They're on both sides. Then I get something that's very important. I get the ratio of E naught plus to H naught plus. And that's equal to what? That's a minus there, I forgot that. It's actually, the minuses will cancel too. It's equal to J omega mu over gamma, isn't it? Please take a careful look at this. Make sure you understand this right here and write it down, because you're going to see this on the final, and you'll be seeing this over and over again in the next, in EMAG 2. Now this is given a special name, and you can almost imagine what it is. what do you call a ratio? E is volts per meter, right? And H is what are the units of H? Anyway, amps per meter, right? So if you got volts per meter over amps per meter, you have volts over amps. And what do we call that? Ohms, right. And this is a characteristic or intrinsic impedance of a media. So write that down. That's the intrinsic impedance of a media. What it does is relate the ratio of E to H in any media. Now I'm going to expand this further. Eta, if we go ahead and we put in what gamma is J omega mu over gamma, which is the square root of J omega mu times sigma plus J omega epsilon, right? Well, you see how that J omega u here and square root of J omega u, it can be rendered like this, the square root of J omega mu over sigma plus J omega epsilon. And this is the one we use all the time. This right here. That's the intrinsic impedance of a medium. And it gives you the ratio of E to H. It's very important. Now, once we have that, we can also go ahead and do, and I'm going to say one thing. This right here is the ratio. This is eta, and it's equal to the square, it's equal to the ratio of E naught plus over H naught plus is equal to the square root of J omega mu over sigma plus J omega epsilon. That's always true. But you'll notice that's the ratio of E naught plus to H naught plus. Now the ratio of E naught minus to H naught minus is actually minus that. It's minus the square root of J omega mu over sigma plus J omega epsilon. And that would be actually equal to just minus eta. So remember the ratio of the waveform in the E to H in the negative direction is negative eta. That's important. Now, furthermore, we're going to keep on going on this one. I'm going to have to erase this part of the board. I know this is kind of just dry theory until you see it applied to problems. A lot of this probably doesn't seem useful at all, but it will be in a second. I'm going to tell you, whoever put this board in, they didn't do us a favor. A regular whiteboard would have probably been cheaper and have been a lot easier. And I don't know why they put this in, to tell you the truth. It's just not, I don't see a reason for it. But anyway, they did, so we'll have to bear with it. Now, the next thing is taking a look at a typical kind of problem that you get. So suppose I said that I had a media, and in the media I had epsilon equal to 10 epsilon naught, and I had epsilon relative, I'm sorry, I had, call it mu equal to just mu naught, and sigma equal to 0. And I have an electric field in this media, in the x direction, with a magnitude of 10 volts per meter, and it's traveling in a plus z direction. I'm just giving specifics. This defines the media it's traveling in. This is the electric field's intensity. That's the direction z. So I want three things from this. First, I want a general equation for E. Then I want a general equation for H. Then I want the actual average power that flows in there. All right? Now, the general equation for E is something that, this is kind of a thing that I didn't give you enough information to nail that down exactly. So some of the things you're gonna need is a frequency. So I'm gonna just say the frequency is 10 to the 6th hertz. You gotta have a frequency. I gave you the orientation, the X direction. And I say it's propagating the Z direction, but I didn't say anything about the phase of the waveform, where it starts, where it stops. So there's gonna be some assumptions. For this one, you know the magnitude of the E field is gonna be 10. It's cosine of, oh, by the way, since sigma 0 is lossless, right? So alpha is 0, correct? Now here it's cosine of what? Omega t, in the general form is omega t minus beta z in the AX direction. We're gonna assume there's no offset phase. So that's 10 times cosine. What would omega be by looking at that? Just tell me what it is.
2 pi 10 to the 6th.
Right, omega is equal to 2 pi times 10 to the 6th. So that means it's cosine of 2 pi times 10 to the 6th t minus beta z. What's beta? How do you get beta? Well, you all agree it's lossless. All right, if it's lossless, do you agree that the phase velocity would be equal to 1 over the square root of mu epsilon? If it is lossless, right? And what is that? That's 1 over the square root of mu epsilon is really square root of 10 down here, right? Times square root of mu epsilon, mu naught epsilon naught. And what do we call 1 over the square root of mu naught epsilon naught? Do you remember, anyone from physics? That's the speed of light. That's c. That's 3 times 10 to the 8th meters per second. That's the speed of light, isn't it? Class? So I can say that v phase here is equal to 1 over, or really c, 3 times 10 to the 8th divided by the square root of 10. That's the phase velocity, right? So how do I get beta? Well, this is just one way. V phase was equal to omega over beta, isn't it? We did that, right? All right, so what is it? V phase is equal to 2 pi times 10 to the 6th, right? Over beta is, sorry. You want beta. Beta is equal to omega over V phase, and that's 2 pi times 10 to the 6th divided by 3 times 10 to the 8th times the square root of 10 on top. And you can see what happens here is I got 10 to the 8th, 10 to the 6th right here gives me 10 to the minus 2. And then I have square root of 10 times 2 pi over 3. And I don't know exactly what that is, but that's calculable. You can calculate that. 6 over 3 is 2 times square root of 10 is about 3. So it's about 7 times 10 to the minus 2, is that right?
6.6.
Okay. 6.6 times 10 to the minus 2, and that would be radians per meter. So now I can say that that's going to be 6.6 times 10 to the minus 2 z, and it's in the AX direction. That's my electric field. How do I get my magnetic field? Well, the magnetic field will be of the form what? I didn't do this, but it's going to have the same form as the E field, right? Because the solutions for the H field had the same phasor form, they'll have the same temporal form as well. There is no alpha because it's lossless, so it's H naught times cosine of omega t minus beta z in the AX direction. So how do we get H naught? The omegas will be the same, by the way. Do you remember? Well, what did I say? The ratio of E naught plus to H naught plus was in, what's it called? Eta, right? And that's equal to the square root of
J omega mu
mu over.
sigma plus J omega epsilon.
All right, now take a look at this. Because it is lossless, sigma 0, right? And you see the J omegas cancel top and bottom there? The J omega here would cancel that. So now this is called eta for a lossless media. It's just the square root of mu over epsilon. And in our case, it's the square root of mu naught over epsilon naught. Epsilon was 10 epsilon naughts, so it's over the square root of 10, right? Now I gotta put this up here. In free space, eta is called eta naught, and it's the square root of mu naught over epsilon naught, and it is equal to 120 pi ohms, or about 377 ohms. And that's the ratio of E to H in free space, or in an air, in things where mu and epsilon are about mu naught epsilon naught, and where sigma is about 0. Follow me on this, class? You'll get this over and over and over again. That means the H field would be what? You agree that this is our eta, right? Isn't it? I'll wait for you for a second. That's the eta in our media, correct? The ratio of E to H, right? Isn't that right? So what is it? Well, eta for our media is really equal to eta naught divided by 1 over square root of 10, right? With me on this? All right, well, what is that? That's the ratio of E naught plus to H naught plus. Or, what can I say? That H naught plus is equal to E naught plus divided by eta, or it's E naught plus, or 10 volts, right? 10 is the magnitude, divided by eta, and eta would be eta naught by 10, or it's 120 pi, right? And it's divided by 10, so this would be times square root of 10 here. Do you agree with me? What is that going to be? Well, I've got 120 pi is 377 into 10 times square root of 10. So can you just give that to me? Thanks, Josh. It'd be 10 square root of 10 over 120 pi. Is that right? And that would be amps per meter. So that means this is 0.827 times cosine of same omega 2 pi times 10 to the 6th t minus 6.6 times 10 to the minus 2z, and it would be in the AY direction, so that's the H field. Now what's the power? Well, from what I did, it would be what? Average power would be 1/2, and then it would be simply what? Magnitude of E naught plus times magnitude of H naught plus, right? Divided by, or I'm sorry, it's this, and it would be in the AZ direction, but that would be 1/2 magnitude of E naught plus, and H naught plus is, again, it's magnitude of E naught plus divided by eta, isn't it? Now I'm putting a magnitude 8 here. I'm going to tell you something in a second. So this is just 1/2 magnitude of E naught plus squared divided by magnitude of eta in the AZ direction, or it's 1/2 times magnitude of 10 squared over what we had is 120 pi divided by the square root of 10 AZ, and that would be watts per meter squared. Now what does that come down to? So I've got 100 by 2, 10 squared is 100 by 2 would be 50, divided by 120 pi, and then times the square root of 10. And if you want, you can just take the magnitude of the E field times the magnitude of the H field and divide it by 2. So if you take 8.27 and divide by 2, that should be the right answer. Oh, I'm sorry. And then you got to divide it by eta. No, wait a second. No, you don't. Divided by 2 is it 4.1375? 0.35? Is that it?
That is
What was it?
0.41941.
0.41941, and that would be watts per meter squared in the AZ direction. So there, we just went and we, more or less, from the E field, got the H field, got the power. Out of curiosity, what's the wavelength? I ask these things and people on tests. These are things that should be fundamental, you should know, but, and there's a lot of ways to get them. People, let's try this. Yeah, what's the wavelength here? How do I get that?
C over.
Well, that's C, it's the velocity. Remember, the velocity isn't C, because mu, or epsilon is 10 epsilon, right? So let's be careful about that. What is the velocity? Velocity is equal to what? It's 1 over the square root of mu epsilon for a lossless media, right? But our epsilon is 10 epsilon naught. So this is equal to actually C, right, divided by the square root of 10 is our phase velocity, isn't that right? So what's the wavelength then? You said it right, but if you would have just used velocity, not C.
Velocity of breath.
Right, it's going to be phase velocity divided by F. So that's going to be C over square root of 10 divided by F, and F was 10 to the 6th. What does that come out to be, wavelength? Meters? That's about right. Here's the way you always like to think about these. We know the speed of light is 3 times 10 to the 8th meters per second, right? And if you're in free space, wavelength is C over F. So 3 times 10 to the 8th over F is wavelength. I know at 300 megahertz, it's 1 meter. At 300 megahertz, C is 3 times 10 to the 8th. F is 3 times 10 to the 8th. It's 1 meter. At 3 gigahertz, it's going to be 10 centimeters, right? At 30 gigahertz, it's 1 millimeter. And then I go backwards. At 30 megahertz, it's 10 meters. And the 10 meter band is a short wave band, I believe. If you keep going down the scale, you can actually see how it goes up orders of magnitude, and you can figure out pretty much what the wavelength should be. So if you're at a gigahertz, it should be about 1/3 of a meter, right? And at 10 gigahertz, it's going to be about 33 centimeters. And that's the way you're sort of getting a handle on it by scaling with respect to what it is. Always start what the wavelength is at 300 megahertz. In your mind, it's 1 meter, and then you can go up and down the scale, because you're going to, a lot of times, have to make like judgment calls in your mind if something sounds reasonable or not, when you see wavelength and frequency and all that stuff happening with measurements. And another thing, technicians aren't, please remember what I say, technicians aren't always people that have gone through a lot of physics. Technicians are people that take measurements and they know how to set up equipment, but most of the underlying physics is obscured to the higher level physics especially. So when you get reports, if you're listening and they're doing field tests, and they're sending back information, and they say something like, and you got 300 megahertz signal, and they got wavelengths of the order of millimeters or something that they're actually observing. There's something way out of line, right? But they don't know it. You have to make that kind of call based on all sorts of more or less assumptions, and you sort of make judgment calls based on your understanding. Okay, now we've got that down. Got that, omega over beta, and you had no questions. Well, the time harmonic field stuff was fairly straightforward. They just asked you to do some simple calculations. We're into chapter 6 now, and I just took you through eta and propagating fields. I'm going to give you one other useful bit of information here, then I'll give you a quiz. And our test is Wednesday, right? Yeah. Just so everybody knows. in general, a nice, easy way of calculating E from H for any kind of waveform is using a vector, these vector identities. Put these down. In general, you can say that the E field is equal to 1 over the intrinsic impedance, and that can be complex, by the way. And then it's going to be, or, I'm sorry, H field, not E field. I'm going to do H first. H field can be gotten, usually the E field is given, is 1 over eta, and then it's going to be the direction of propagation crossed into the E field. Now he has these down here. It's a unit vector in the direction of propagation. This is on page 327 at the bottom. And E can be gotten as eta times A propagation crossed into the H field, and he'll have a minus sign there. I don't think he reverses the crossing order. Yeah, he's got the minus there. Now, here, AP is just a unit vector, in direction of propagation. And so these are vectored field quantities, and this works when you're talking about propagating fields. This only is for propagating fields. Like plane waves, things that are launched. They're not associated with the electric field that has to do with electrostatic energy or the magnetic field that has to do with magnetostatic energy. This is when a wave is launched and it's no longer, those photons are gone forever. They're not coupled to the actual capacitor or inductor. Think about this. So if you wanted to do a quickie here, suppose I give you this. I give you H is equal to 10 amps per meter. I'll give you eta is equal to just 200 ohms. And I'll say it's propagating in AY direction. And I'm going to say it's propagating in the AY direction, but H is in AX direction. So H is in the X direction, Y is in, it's propagating in the Y direction. So first, what would be an equation for the H field? Assume it's lossless for now. Well, in general, H, the general form of the field in the phasor domain would be the magnitude of the H field first, which is 10, right? Then it's propagating in AY, so there would be E to the minus, I can put minus J beta Y here, and because this has to be the direction of propagation. Then it also says that it's in the Y direction, and it has an AX connotation, so then it would be AX here. You agree with that? I didn't put a frequency down, so remember beta in general for a lossless case, if it's lossless, and this is, beta is equal to simply omega times square root of mu epsilon if it's lossless, and I'll tell you how I get that. I'll put it right here. You know how gamma in general is equal to the square root of J omega mu times sigma plus J omega epsilon? And that's equal to alpha plus J beta. Well, if it's lossless, if sigma is 0, then gamma is just equal to J beta, and that's equal to J omega mu square root of mu epsilon, or beta is just omega times, beta is just equal to omega times square root of mu epsilon. And that really is omega divided by the velocity of propagation in the medium. Now, I didn't give you a frequency, so you can leave this just beta. So how do I get the E field? Just take a look at that.
Can you read that? It's minus eta, right? So it's minus 200, right? What's the direction of propagation, a unit vector in the direction of propagation?
X,
Can you read that? AY.
no,
Sorry, it's oriented in the x direction. The h field has got it. The vector senses in the x direction for the h field, but it's propagating the y. Follow me? So it's times ay, right? Then it's going to be crossed into the h field, right? Which is 10 e to the minus j beta y ax. So what are we left with? We got minus 2,000, correct? E to the minus j beta y, correct? And what's ay crossed ax?
negative AZ.
Right, and so since it's negative az, this becomes plus, and that's getting the E field from the H field. Understand, everyone? So now we've gone through and we got time domain form and frequency or phasor domain form of E and H. We've got the power. I'll show you how to calculate the power density, wavelength, phase velocity, how you can calculate gamma to get alpha plus j beta. And in general, what we're doing here is we're characterizing a media in terms of its the electric field behavior completely with this method. And you're going to see where that becomes very useful with sources in different regions when they match together. But for now, I stop here. I got to give you a quiz. So.